they will start. Yeah.
Okay. So welcome to attend Professor Mark Fontcave presentation, lectures, and let me give a brief introduction to Professor Mark Fontcave. Professor Mark Fontcave is a professor at Collège de France. He is a distinguished member of French Academy of Sciences, Academia Europaea, and Royal Swedish Academy of Sciences. And also, he is the senior fellow of Hong Kong ICE, City University Hong Kong. And to save time, now today his lecture title is From Nature to Chemistry, Bioinspired Catalysis for CO2 valorization. Oh, sorry. So to save time, so let's welcome Professor Mark Fontcave.
Thank you so much. I'm very glad to be here. Thank you for the invitation. So I will take this opportunity to tell you a bit about one aspect of the energetic transition, which relies on the technologies to make alternative fuels in a way. And I will talk about a very specific approach. That's why I'm talking from nature to chemistry, because I want to show you how actually nature makes fuels for the cells, of course, not for the cars. What you have to really consider is that fossil carbon, oil, gas, coal, is not only a source of energy, it's also a source of carbon. And we need carbon in our societies, I mean, to make this kind of compounds, fuels, plastic, fibers, solvents, insecticide, pharmaceuticals. You know, a drug is carbon-based, is an organic compound, and you need carbon. Today, all these, it's something like 100,000 compounds in the chemical industry, which rely on three sources of carbon that you can see here. Natural gas, it's quite difficult to, where is it? Here? Je ne vois pas parce que j'ai un problème de... Ah oui, voilà, c'est terrible ce truc, je pointe là et... Yeah, so natural gas, oil and coal. So tomorrow, if we get rid of that, we have to find alternative sources of carbon. And it's not so easy. I mean, there are so many, there are so few such sources that you have to list them and see what you can do. And basically, you have to rely on either biomass or waste and CO2. And the idea here is of the research is how we can use CO2 that we capture somewhere, in particular from the industrial plants that emit large concentration of CO2, and then do something with CO2. Not only sequester it, but make chemistry on it and make something useful from CO2. That's the point. Again, I want to. So the idea is to combine basically CO2 and water, make them react together, and make all sorts of compounds, chemicals, fuels, polymers, and of course this chemistry here, these reactions require energy. So of course you will not use fossil fuels to do this. You want to have renewable energy, and you basically what we do in my lab is trying to couple sun energy with these type of reactions. So that's the purpose of the research. Now, that's the first point. The second point is that while people have tried to do this reaction extensively using different types of devices, catalysts and so on. I want to show you today a specific approach which is based on nature. So in fact, if you want to do CO2 conversion to a useful compound, you can realize that this is exactly what some cells are doing here. Yeah, sorry, I'm not going. Yeah, here. So these are microalgae, and these microorganisms are very clever to take up CO2, mix with water, use solar energy, and do a lot of interesting compounds. Actually, all the biomass that they need, sugars, lipids, proteins, and so on. And this is because they have the potential to do photosynthesis. There is one part of the research where people use the cells by themselves. They use a cell factory to make compounds. I will not show you this. Then the second approach is considering that within these cells, you have interesting enzymes that do the chemistry. So one approach is to understand which enzyme is doing the chemistry, purify it, characterize it, and use it in a biocatalytic system. So enzymes can be used to do the conversion of CO2. Then the next step is, if you understand clearly what the enzyme does, the chemists have the potential to mimic the enzyme, make a simple system that is inspired by the natural enzyme. And what we develop is bioinspired catalyst, which can do the chemistry that is done in these cells. That's the objective. Very challenging, but that's the idea. And then when you get this bioinspired catalyst, you can even go back to put them into proteins, not necessarily an enzyme, but to find a good protein that would take one of those bioinspired catalysts, and then you create artificial enzyme. You create new enzymes, which are not present in cells, in natural cells, but you invent from this bio-inspired approach. And the last step is, if this enzyme is good, you can reintroduce it into a cell, and you make an artificial cell that has the potential to use this artificial enzyme and make the chemistry that you want to do. For example, I will tell you that we are interested in making CO from CO2, or ethylene, or ethanol. So we could take a cell that doesn't know how to make ethylene. I mean, there is no cell doing ethylene. You know, ethylene is a very important compound for the chemical industry. It is the most produced in the world. It's 200 million tons of ethylene, and it's so important because it's the precursor of a lot of polymers in the chemical industry. Polyethylene being the direct one. Yeah, so that's the strategy we want to develop, and when we have this catalyst, and I will explain why it is important to have a catalyst, the idea is to develop this, which is an electrolyzer, simply an electrochemical cells, in which you put CO2, water, and you fuel with renewable energy, low carbon energy, like sun or wind. And inside of this machine, carbon, oxygen, and hydrogen atoms combine to make interesting compound that would be useful for the industry. It can be plastics, it can be, precursors of plastics, feedstocks, fuels, and drugs, pharmaceutical drugs. And the interest of the advantage of this strategy is that, of course, the CO2 that you put in, you take it off from the atmosphere. The second thing is that uh, the energy you have used here from the sun and the wind are now in the molecules, in the bonds that have been created. So you convert, for example, wind energy into chemical energy. And the good thing with this conversion is that, for example, the electrical energy from the sun, if you don't use it, you lose it. So it's nice to have a way to store it somewhere. So for example, if you convert sun energy into ethanol, which is a liquid stable that you can store and use it anytime when you need it. So it's a nice way to store the intermittent energy, which is a major problem. And of course, by doing this, you really make organic compounds which are not deriving from fossil sources, oil and gas. Yeah, so now come a little bit of real chemistry, I would say. So the machine I mentioned is an electrochemical cell, which is very simply described as a cathode. That's where you make the conversion of CO2 into something useful. It can be ethanol or ethylene. And at the anode, you have an oxidation. So a reduction here, an oxidation at the anode where you oxidize water into oxygen. And the thing is that when you look at the reaction at work in these electrodes, so at the anode you have this reaction, which implies 4 protons, 4 electrons, and these are a series of CO2 reaction to make CO, formic acid, ethylene, ethanol, and what you realize here that these are amazingly complex reactions involving 12 protons and 12 electrons, and for that reason, these reactions are very slow, are very kinetically constrained, and you need catalysts to do that. So you have to use catalysts to decrease the energy barrier between the reactants and the products. Otherwise, you won't get enough product, I mean, in a reasonable time. So one of the key things is to find a good catalyst to catalyze multi-electron transfer, multi-proton transfers. It would be nice to use non-noble metals because they are cheap and abundant. And of course, you have to work on the selectivity of the reaction, the stability of the catalyst, and the cost of the whole machine. The selectivity is really crucial because, as you can see here with the blue equations, mixing protons and electrons with CO2 can give you a lot of different products. So you have to find catalysts if you want to be selective for one product. And the other problem is the last reaction here, where since you need protons and electrons, you cannot avoid making hydrogen, which you don't want in that case. You lose energy to do hydrogen, and this is something also that has to be addressed. Yeah, so one class of catalysts are molecular catalysts. So there are not so many actually, but there are some of the catalysts that have been developed in the last, I would say, 40, 50 years, because actually it's a very French story actually, because the pioneer in this field are Jean-Marie Laine, Alain de Ronzier, Jean-Michel Savéan in Paris, Jean-Pierre Sauvage, who got the Nobel Prize, as Jean-Marie Laine, Sauvage more recently. Yeah, so I don't know why. I mean, French scientists were so interested in this catalysis, but so these are some of the complexes. Okay, so I will now tell you another story. I told you that I'm interested in mimicking nature. What we discovered in a way, because it was not so much considered some years ago, what we discovered is that in some microorganisms, there are enzymes which catalyze CO2 conversion. And it's interesting to, we do molecular chemistry in my lab, we do material science, but we also do enzymology. So we purify enzyme and we characterize them, we crystallize them and so on. So then you look, you ask the question, what type of catalyst for a catalyst in biology is an enzyme? What kind of enzyme nature uses to do CO2 conversion? And in fact, there are not so many. The first class of enzyme that I will discuss is what we called formate dehydrogenase. Le truc s'échappe, il revient, hop. Non, il est reparti, voilà. Formate dehydrogenase, which convert CO2 into formic acid, which is an interesting compound to make. So when you look at how nature does this chemistry, it's amazing that the only metals that they use in these enzymes are molybdenum and tungsten. I mean, no chemist would select these metals spontaneously to do catalysis of CO2 reduction. But this is what nature has selected. This is quite intriguing. And more specifically, so there is an X-ray structure of this kind of enzyme. You see, if I succeed to recover the, yeah. So you have the molybdenum here in blue, and what you see around the molybdenum in yellow, it's very yellow around the molybdenum atom. These are sulfur atoms. So it's very sulfur coordinated, and the sulfur come exclusively from this biological compound here, which is molybdopterin, which provide two sulfur to coordinating, to binding the metal. Then you have a second class of enzyme that we call CO dehydrogenase. In this case, the CO2 is reduced into CO. And here, again, we find two classes of CO dehydrogenase. One, which is shown here. Where is it again? Yeah, here, where you have one molybdenum, you have also the same molybdopterin here, and this molybdenum is coupled to a copper atom bound to a cysteine of the protein, and you have a sulfur bridge. And then you have a second class of CO dehydrogenase, which is nickel-iron based. It's a very complex structure, iron-sulfur cluster with nickel and iron. So when we started our research, we studied this enzyme first, and then we said, okay, we should mimic these active sites, because these exactly the sites where the chemistry takes place, this reduction of CO2 into formic acid and CO. And there was absolutely, so we started in the middle of the 2010, 12, and there was absolutely no mimic of this enzyme that were catalytically active, and I want to show you some results. The first thing we wanted to do was to consider the molybdopterin, which is this natural ligand, and we wanted to synthesize it. We failed. Nobody has succeeded in synthesizing this molecule. This is quite intriguing, but so we decided that we should synthesize a molecule that is as close as possible to this molecule. Remember that this is a tricycle. There are 3 cycles in this molecule, and in the center here, which is a pyrazine cycle for the experts in chemistry, it is reduced. It can be at different redox states, but this will be an important point. So in the literature, people had, I mean, great inorganic chemists like Dick Holm in the States, Sarkar in India, Tatsumi in Japan, had synthesized such molybdenum or tungsten complexes with sulfur coordination. These are some of the ligands that were used. These are more complicated, but no one resembles the biological compound. So that's what we did. I have no time to, of course, discuss. It's an original synthetic pathway. So we have been able to synthesize this molecule. It's really a mimic of the biological compound, even though you see some difference. But we have there 3 cycles. We have a pyrazine ring here. We have this oxygen atom. It's a pyrene ring, and we have the 2 sulfur to bind the metal. So we have been able to synthesize the complex here. So we have synthesized this complex by combining the ligand with the molybdenum. So it's a very good mimic of the active sites of formate dehydrogenase. We have been able to crystallize it to get its structure, and we see very much similarity with the natural active sites within the protein. I have no time to detail the different aspects of the cluster. Then, as I told you, you see that here in the biological molybdopterin, the central cycle is hydrogenated, which is not the case in our synthetic molecule. So briefly, we have hydrogenated this central cycle or reduced it. It is described here, and it has been very difficult. In fact, it took years to do it, because as soon as you touch this central ring, you destroy the whole molecule. So it was very difficult to get the real compound. So then, when we had all these complexes, we studied the photochemical reduction of CO2. This was an assay that is described here. We irradiate. It's a lamp that can be used to irradiate the solution containing our catalyst, a photosensitizer, which is here this ruthenium compound, a source of protons, and a reducing agent, which is this molecule. It's not necessary to get all these details, but this is an assay to really evaluate the catalytic properties of the new molecules that we create to do photoreduction of CO2 into something. And I want to just show you the first, and actually I think the last, functional biomimetic formate dehydrogenase system. For doing this research, we used the three complexes that we synthesize, the first one and the one here in which the central cycle has been modified, as you can see here. The only difference between these 3 complexes is the central ring here. And what we observed is that these catalysts were able to generate carbon monoxide and formic acid, but still too much hydrogen, which is a problem. These results are for this first complex, but amazingly, and we still do not understand, and we want to understand why this central cycle is so important. Because when you look at the result, when you look at the selectivity, so you compare the CO2 reduction to the proton reduction to do hydrogen. You see here, sorry, this, the best, you have big differences, so the best system is the one which has the fully modified central ring. So yeah, so the reason why nature has modified this central ring is not clear, but here what we find is that it serves to make a very selective CO2 reduction as compared to proton reduction. Yeah, I have no time to go into these details. So this research was done by some of these people. So you can see here on the top of the Collège de France. Behind you have Notre Dame under reconstruction. So Yoon and Maria coordinated this work, and two PhD students contributed to the synthesis, Jean-Philippe and Thibault, the synthesis of these compounds. And we did some DFT calculation with Tanya. I want to show you now another system that we mimicked, which is probably the most difficult system to mimic, which is the photosynthetic system. So I'll try to explain. So here on the left, you have the photosynthetic system. I don't show you the protein around. I show you all the cofactors present in this photosynthetic system. So all these molecules around are there to collect photons from the sun and create excited electrons that go away and holes which accumulate into an inorganic metallic site, which is composed of manganese in purple and calcium. It's a cluster, and this is the place where photosynthetic organisms like photosynthetic bacteria, cyanobacteria, and also in plants, do water oxidation into oxygen. So this system functions thanks to molecules, organic molecules that collect photons from the sun, and this cluster. So we wanted to mimic this and have a system that is synthetic, that makes water oxidation to oxygen. And so we selected this hybrid material that is represented here, which is a metal organic framework. Chemists know that quite well. The interesting thing is that you have it's a coordination polymer where you have nodes here which are basically not active. You have linkers in which you can bind catalyst or photosensitizing units. Specifically here, I want to show you what is the material we are using. This is made of a cluster, a zirconium cluster, which is here. We have a porphyrin. This is an interesting molecule because it has the ability to collect the photons of the sun that are here between two clusters. So you see here, these lines are the porphyrins. So this system is very rich in porphyrins. Non, c'est pas ça. Oui, c'est ça. And you have pores also. You have some space here, and that's where, in the next step, we were able to bind this molecule, this cluster, this cobalt-based. You remember that the natural photosynthetic center is a manganese calcium, 4 manganese and 1 calcium. Here, our mimic was a cluster with 4 cobalt. So, you know, that's the way chemists do. I mean, we get inspiration from nature, but we are not, we do not have to stick to exactly the same thing as what nature does. You would say that a real biomimetic would be with manganese and calcium. Some people have tried that, but here we took this cobalt cluster because it was good at doing the water oxidation. And the good thing is that when we combine the metal organic framework that I described previously to this cobalt cluster, this guy went inside the big pore and ended up, because of interaction with the cluster, the zirconium cluster, close to the porphyrin, so which favors the electron transfer from the excited porphyrin, electron going into the cobalt to do the, or electron going from the cobalt to the porphyrin to do the water oxidation. So this is a movie, but I have no time to go into it. But this is to show you that, you know, here, like in the natural system, you have a porphyrin which can take the photons from the sun, get excited. An electron is going somewhere, and from an electron acceptor, and you make a hole here, and then the electrons are going from the catalyst to the porphyrin, and that's where water binds and is oxidized by 4 electrons to oxygen. Okay, I just want to show you that this is a very stable system. Here you have a curve showing the kinetics of oxygen formation. So the mechanism. The mechanism is that you excitate with light this material. When it is excited, it gets 1 electron out with this molecule which accepts an electron, and then the electrons are going this way and water is oxidized to oxygen, and we follow the generation of oxygen, and when all the electron acceptor is consumed, it stops. And it restarts again quite the same. This is 3 runs. And here we can see that when we have consumed this molecule, we add it and it starts again. So it's a very stable system. And as you can see here, that figure here is to show you really what is a bio-inspired system. This is the photosynthetic system that you have in plants and so on. So it's very complex. There is something like 30 or 40 proteins. There are 20 different cofactors to collect the sun. You have the manganese calcium cluster and so on. This is a simplification of that. And this is our, that's where you have the photon collectors. And this is where the water is oxidized. And what we have done is a much less complicated system with this mimicking the complex one here, the porphyrin here mimicking all this ensemble, and our cobalt-4 cluster mimicking the manganese calcium. And it works. So that's the kind of thing you can play with if you are interested in doing biomimetic chemistry. Okay, this was a very important part of Grégoire's PhD thesis, and this was developed with my collaborator Caroline and Anne, a collaborator in Versailles. Okay. Now I go a step further, and you remember that we can do artificial enzymes by combining proteins and synthetic compounds to make a new enzyme. So a few years ago, we decided that we should try to do a CO2 reductase enzyme. This, I mean, an artificial one was not existing before, and then, yeah, that has been a project for some years. Again, I remind you that in nature there are only the formate dehydrogenase and the CO dehydrogenase enzymes using molybdenum, molybdenum copper, and nickel iron. Yeah, so we were interested with this enzyme, also quite complex, proteins carrying this active site. You remember molybdenum, copper. We discovered a protein here which has the ability to bind this cluster. It's not exactly the same as here, but you can recognize a molybdenum, sulfur, copper as in this enzyme. So we were, actually, we have the crystal structure of this protein, but in the absence of the cluster, because we could not get a structure with a cluster inside, but we had evidence that the cluster binds, and specifically in this position, because in blue it's a very positively charged space, cavity in which this complex, this cluster, which is very negatively charged, can nicely go into this site, and that's what you see. You see here. This is a model. This is a protein modelization, and you see that this cluster is binding here because it has a lot of electrostatic interaction with arginine and lysine residues. So then we decided, okay, we will make this protein, and it should be nice to do CO2 reduction. It's exactly, it's close to the CO dehydrogenase active center. In fact, it was a complete failure. This has absolutely no CO2 reduction activity. It was unfortunate. I forgot to say that what we did is that we found that this cluster, for this cluster, you are not limited to molybdenum and copper. You can do, in place of molybdenum, you can do tungsten, and in place of copper, you can do iron, nickel, cobalt, zinc. So we had plenty of possibilities to study, but none worked, and there was no CO2 reduction. The good thing is that it was a fantastic system to do proton reduction. So it's a kind of artificial hydrogenase. I didn't say anything about hydrogenase, but in living cells, there are enzymes called hydrogenase which are able to convert water into hydrogen, which is also very interesting. And this is an artificial hydrogenase which works very well. And we could, this is hydrogen production. It's not necessary to go into these details. But the very interesting thing is that you could manipulate the metals to do different combination, and you had different activities. And the most active system was the molybdenum iron, which is in here, this point here, which is the most active system. And we have one of the best artificial hydrogenase by doing this. So this is completely by chance. I mean, we didn't want to do an hydrogenase, but we got there. And this is, yeah, sometimes you are lucky and you get this. Yeah, this is, I don't need to do, but by doing some calculation, we understood a little bit why it does so well proton reduction rather than CO2 reduction. In fact, we have shown that this type of cluster with these sulfur atoms are very good at binding hydrogen atoms. And this is a very nice configuration when you have one hydrogen atom here and there. to make hydrogen-hydrogen bond formation, one H reacting with another H. So this is a very well designed to do proton reduction. Instead, when you try to calculate whether this hydrogen can react with CO2, the energy barrier was very high. You can see here, 16 kilocal per mole, as compared to about 5 kilocal per mole for the proton reduction. So the proton reduction is much favored. Yeah, so this work was done by Raphael here with these collaborators. So Raphael will defend this work next week, actually. Now, I want to show you one real artificial CO2 reductase. So what we did is that we took this protein here, which is a heme oxygenase, but forget its real function, and combining this protein with a cobalt porphyrin, which is not natural. Remember that the heme has iron instead. There is no cobalt porphyrin in living cells. So we added a cobalt porphyrin for a reason that I have no time to explain why we selected it, and we succeeded to get this cobalt porphyrin bound in this protein. We got a crystal structure of the cobalt porphyrin protein, which is shown here. You see the electron density of the cobalt porphyrin with a water ligand and a series of water molecules that connect the cobalt to the surface of the protein. And furthermore, we were very lucky because we designed an experiment at the synchrotron to study the protein crystals under pressure of CO2. And we got a structure of the artificial protein with CO2 here, which is, because of the resolution of the structure is remarkable. It is, I don't know where is it, 1.8 or 9. So we could see the molecule, and this gives you one state of the catalysis where CO2 binds to the active sites. And the results is that this is indeed a CO2, artificial CO2 reductase. This enzyme, which is again not natural, is able to do CO2 reduction quite selectively towards formation of CO that you can see here with some hydrogen, but not too much as compared to the data I showed before. I have no time to explain the mechanism. It's not necessary here. We use this photosensitizer, a copper-based molecule, to collect the photons of the light. And the activity is quite remarkable. This is, I mean, since then there are some other CO2 reductases, but this one is, I think, the most active artificial enzyme to do CO2 reduction. Okay, I want to finish on this aspect. In general, when you mimic enzymes, you do molecules, because an enzyme is a molecule. It's not a material. It's a molecule. The active site is a molecule. So you translate the information you get from an enzyme into molecules. What I want to show you here is that, and this is something that has been rarely developed, is can we mimic an enzyme by doing a material, by doing a solid? Again, you recognize these molecules. So these are cytochromes which contain this heme, this iron porphyrin. That's what you find in myoglobin, for example, or hemoglobin, and this is where oxygen binds, allowing you to respire. But this type of systems in biology are known to be very good electron transfer systems. So we were interested in this, And furthermore, Jean-Michel Savéan in Paris also showed that synthetic iron porphyrins here are very good catalysts for CO2 reduction. So we thought, how can we mimic this type of biological system into a solid? And I want to show you the last result. I will not show you all the steps toward this last system, because I want to show you a copper-based systems. So here, we wanted to have a solid with this type of coordination on the surface of the solid. And what we have done is to develop a material in which it's a kind of graphite-like carbon-based material, which is doped with nitrogen atom and copper atoms. You can do it also with iron. And I don't tell you how we make it and how we characterize it, but this figure tells you exactly what type of material we have. The big surprise came when we discovered that this material is very good at doing, I could just again. So you see, some copper atoms are surrounded by 4 nitrogen atoms, exactly like in the natural iron porphyrin. So the very interesting thing is that when we do CO2 electro reduction, we found that this material was very good at producing ethanol, which is in black here, with very good yield. Ethanol is a very important product to make from CO2. I mean, it is a fuel. It can be used in the industry and so on. And when we started from CO, we did CO reduction. We had almost 70% Faradic efficiency. So it's a very good system. And I want to tell you a little bit why it was just impossible to understand. In fact, the theory tells you the following. This is a kind of dogma. When you have a solid material, copper, for example, and you have CO2 reacting with it, you have 2 pathways. One pathway is the formate pathway here, leading to formic acid. And here you see that CO2 binds through the oxygen atoms. And when you go to formic acid, you cannot do anything else. The second pathway is when CO2 binds through the carbon atom. And when you are in this situation, you lose a water molecule, and you get 1 molecule of CO now. 1 oxygen has been lost, 1 molecule of CO into the surface. And then you have 2 situations. Either CO is released, and you generate CO, or you have several molecules of CO at the surface, and the only way to do ethanol is if you have 2 copper atoms adjacent to each other, in which you have 1 molecule of CO on each. And that's where you can make the carbon-carbon bond. So what happens when you have only a single site? How can you make CC bond? That was the point. In fact, we did a very interesting experiment. So we set up an experiment at the synchrotron, Soleil, where we exposed our cell, electrochemical cell, to X-rays to characterize the material, the catalyst under working conditions in operando. And what we discovered, I don't go into the details. What we discovered, I don't go into the details of the analysis, but what we discovered is that the copper transiently gets out from the site and make very small clusters, and these clusters are the active species for the CO2 reduction. And here you can understand why you can do CC bond formation, because here you have adjacent copper atoms. The most amazing thing is that this was possible I mean, this situation is only transient because when you stop the reaction, the cluster disintegrates, and each atom is going back to the initial site. So at the very beginning, when we did characterization of the material before and after electrolysis, we saw the same material. So we did not understand what happened. It's only when we did this kind of experiment that we discovered that there is something occurring transiently which explains the reactivity. Okay. Yeah, these are the people who contributed to this field, and in particular, Juan here is an engineer in my lab at the Collège de France, and is a great collaborator, and Dylan was the PhD student that did this work. Okay, this is my conclusion now. I've tried to show you some examples of the Bioinspired approach that we use quite heavily in my laboratory, doing molecular catalyst, artificial enzymes, solid materials, always for CO2 reduction. Yeah, so it's really fun. Actually, for a a chemist creates molecules, so it's always so nice to see a new molecule appearing from your laboratory, especially if they are mimicking complex biological systems like enzymes. So it's really fun. Yeah, it's of course very challenging. And since the systems we are mimicking are so complex, yeah, it's very difficult. On the other hand, the philosophy of bioinspired chemistry is not to make a too much complex system. If you do something that is as complex as an enzyme, just use the enzyme. Don't use your material. So you have to simplify it. That's the key thing. You have to simplify it without losing too much of the performances of the biological system. For example, one big simplification that we do when we do a bioinspired catalyst, not an artificial enzyme, but a bioinspired catalyst, for example, is we get rid of all the protein, as if the polypeptide chain was not useful. It is, of course, useful and provides important properties, but we remove it and still we can have some activity. So we have to find the right balance between simplification and reality. One of the things that we have provided that you can do bioinspired chemistry and not being limited to molecular system. It's quite funny to try to think how I can make a solid material that mimics an enzyme. It's not trivial, but it's funny. Yeah, this is true. You rarely get what you expect. Yeah, so it means that the simplification that you have provided is maybe too much. Yeah. I must say that so far there is no real application of this science available. So these systems are really interesting for synthetic chemists, but still a bit far from the application because you have to improve the efficiency, the selectivity, the performances, and so on, the stability. My last slide is this one. It is from Jean-Marie Laine. I find it still really stimulating, inspiring. So here, if you plot the complexity over diversity, you would say that biology is here. So diversity is limited. You have only 20 amino acids, you have 4 nucleic bases, and so on. But the complexity can be huge. The chemistry is more like that. Here, I mean, you can do any molecule you want. So the diversity is big, the complexity is limited. So this scheme here was done by Jean-Marie to tell to people, if you want to do something useful in chemistry or biology, you have to go there, the empty space. So increase this border, shift this border. Yeah. So I would say that, that's what I put here. I mean, synthetic biology, metabolic engineering, synthetic cells, that's the way to move the border to the right. And for the chemist, doing bioinspired chemistry, as I showed you, is a way to move also this border up. Artificial enzymology, enzymatic engineering, that's what I told you today. And then I stop here, and I hope you were interested by this approach, and I am ready to answer your question if you have. Thank you.
So thank you, Professor Mark van der Keep. So let's go to the Q&A session. So any question from our audience? No? Oh, Professor Yu.
Thank you for the great talk about, especially the first part about the biomimetic systems. And for your molybdenum system, my question will be, how is the stability? Because the molybdenum can undergo the hydrolysis if you have the energy input.
If you're talking about for example, the molybdenum complex that I mentioned, we do electrolysis for something like 20-24 hours, and it's very stable. So the stability is fine. The problem is still that the selectivity for CO2 is not high enough. We have still quite a lot of hydrogen for the reason I mentioned, the ability to do proton reduction. But stability is okay.
And also the other question would be, like, in the biologists, the best thing is that the overall potentials usually will be quite low, close to the thermodynamic limits. So what about your system? Is it still?
No, here is a big difference. Indeed, the enzymes that have been actually studied on electrodes are reversible systems. So the overpotential is very small. Here, none of these systems are reversible. So they don't do formic acid oxidation to CO2 or CO oxidation to CO2. So you have to apply a very high overpotential to do it. Yeah. So the overpotential is something around 600 millivolt or something like that. Yeah. Yeah, which is of course a cost, an energy cost. That's the kind of thing you have to improve if you want to develop this kind of molecular catalyst. Yeah.
Mm-hmm. Yeah. Thank you.
So any other question?
Thank you for a very pleasant lecture. Even though it's not at all my field, as you know, but I have a question. So if I understand well, what you're trying to do is to approximate complicated molecules by simpler ones. But what is your measure of approximation? When can you decide that a simple molecule is close to another one? What's your measure of proximity somehow?
Yeah, for example, si je reviens voilà. Non, pas ça. Yeah. So what we know, for example, what we know about enzymes in general, metalloenzymes. So we are exclusively interested in metalloenzymes. They are not all metalloenzymes. They are enzymes without metals, of course. So what we know is that a metalloenzyme is a combination of a huge part of polypeptide chain, okay, protein, which provides cavities and so on, and a small space where you have the metal and a few molecules around. And we know that the chemistry that takes place with this enzyme is there, exclusively there. The metal binds the reactant, activate them and make the reaction. So the first approximation we do as a chemist in general is that the key is the metal center. So if the metal center, so that's why we reduce it to this image, and we try to mimic only this part. And this is not stupid, even though you remove a huge part of the enzyme. It's not stupid because the metal is very much affected by what we call the first coordination sphere, so the first molecules around here, which are amino acid in this case, maybe a little bit more around, and we try also to go there, but not further, even though nature has probably selected the whole thing to make it better than what we can do. So that's the type of approach, and it works. I mean, in general, it works. Not always, as you have seen when I did this molybdenum copper cluster, molybdenum copper molybdenum. It didn't do the chemistry that the enzyme did, but that's the rationale. That's the rationale. Yeah.
Thank you very much.
Okay, thank you. So,
Yeah.
Okay, thanks, Professor, for your wonderful talk. Yeah, first my question is, this is the real enzyme. They because they are quite like auto-soluble because there are so many proteins. But like the artificial enzyme, it is some like organic compound. So what kind of solvent you use? Like you use auto-organic solvent?
Yeah. Thank you for this question. Here, I mean, the enzyme, the natural enzyme, are soluble in water.
Yeah.
Okay. And for the future, electrochemical devices that will be on the market, the solvent of choice will be water, probably. I don't think that in the future we will have electrolyzers with organic solvent. Where you are right is that sometimes the biomimetic system that you make is not soluble in water. And very often it is only soluble in an organic solvent, which is a problem. But the good thing is that when you succeed to put this molecule insoluble in water into a protein, then you make this system soluble in water. So it's a way to solubilize the organometallic system that is not soluble in water.
Yeah, but I think in your system is you didn't put the metal center into the enzyme, right? You just mimic the enzyme. It's not the real enzyme. You use it here.
Of course, yeah. That's the fascinating. The fascinating thing is that this artificial hydrogenase that I mentioned, or the artificial CO2 reductase with the cobalt porphyrin I showed to you, these are not. This is not existing in cells.
Okay.
So it's a completely. That's why we call it artificial. But it's an enzyme because it do catalysis, and the next step would be. That's something we did in another project, but would be now to put this molecule, if it is interesting because good activity, stability, and so on, to put it in some cell, and then create a cell factory which does a chemistry that is not done by nature.
Okay, thanks. Yeah, my second question, you have one unexpected result, that is you get hydrogenase, right? It's very high efficient for the hydrogen release. But we know in nature there are three kinds of hydrogenase,
Yeah,
like ion, nickel, and the mono ion. So compared with the natural enzyme, which is more efficient compared with yours?
Yeah, it's less efficient.
Oh, it's less efficient.
Yeah, it's less efficient, not so inferior, but it's less efficient. The problem is that the natural enzymes, the hydrogenases, are very difficult to purify, to use. They are sensitive to oxygen. So, that's why sometimes in the future, we may really use this kind of artificial enzymology to make technological systems, because all this, actually I should have said it, but all the biological system I mentioned to you, the CO dehydrogenase, the formate dehydrogenase, they are very, very difficult to get pure, to put it on a cell, they are very sensitive to oxygen. So my opinion, my clear opinion, is that these enzymes by themselves, they will not be used in future technological devices.
Yes,
Too
you are right,
complicated.
yeah.
That's why this approach may have some future, because not only you simplify it, but at the same time you try to make it more stable and so on. Yeah. Even though in terms of activity, it's less.
Yeah, okay, thank you, thank you.
I have a question about the theory. To which extent can you use ab initio calculation to try to orient your work? And you mentioned DFT, for example. Are you working with condensed matter physicists who can help you in this?
Yeah. Indeed, calculations, theoretical computational chemistry has become a key component of all this research. So I didn't mention it, but all these systems, we collaborate, and sometimes we have people in my lab doing the computational chemistry. So what is it exactly? The first step is to mimic the system itself, and to model the system, which is very complicated. And here, indeed, physicists are more and more involved in that domain. Actually, I have started some collaboration with Antoine Georges, and I came to, he invited me to meet his colleagues in New York, in his institute, and they have a big plan to invest this type of systems theoretically. So this is, but it's not yet completely developed. For the moment, it's mainly DFT calculations with quite simple models of the systems. The molecular systems are quite easy to model. The solid materials are much more difficult.
And what about artificial intelligence?
Yeah,
I
thought you would ask me the question after this. Yeah, we are at the very beginning. In this field, maybe there is something like 1 or 2 papers, not more, in which people have, indeed through artificial intelligence, tried to tell us what would be the best catalyst to do this CO2 reduction. Yeah, it's not very well developed. The problem is that there are not so many data, in fact. I think this is a limitation of the artificial intelligence. And the reason why it is so, if I can take just 2 minutes to tell you, in fact, you remember the different products we can have from CO2. Either we have formic acid, or CO, or CC coupling to make more interesting molecules like ethylene, ethanol. In fact, it's amazing, it's sad actually, there is only one metal that can do CC coupling, it's copper. We have tried, not myself, but all the people in this field have tried all the metals of Mendeleev table. The only that can do ethanol and ethylene is copper. So everybody is working on copper, which is a pity. But furthermore, we have not so much data to really apply the artificial intelligence approach, because we have only the same type of copper materials and so on. So it's not a great diversity. So it's difficult to go further. But people work on it.
And I have a last question. One of the important problems now is to try to store this solar energy into fuels for transportation. What do you think is the best route to try to do this kind of experiment, or to produce hydrogen by electrolysis?
Yeah, okay. Indeed, what is behind all this chemistry is to, I mentioned polymers, but also fuels. Make alternative fuels from CO2. There are basically two approaches. The first approach is to do hydrogen and then hydrogenation of CO2. So you make CO2 reacting with hydrogen. So you have the storage step is the first step, in which you store the solar energy into hydrogen. And then the CO2 plus hydrogen is not, it's just a thermal reaction. You do methanol, you do Fischer-Tropsch reactions and so on. And the second approach is the one we use, which is putting directly the electricity, the electrons, into CO2 and water, and not doing hydrogen in between. So there are different philosophies. For example, of course, I'm working in collaboration with big companies like Total Energy and Veolia and so on, and their preferred approach is mine. Because, in fact, if you do this in two steps, it implies some capital cost, because you have two machines, you have two reactors. You have the first reactor to do hydrogen and the second reactor to do hydrogenation. Here, you put all together electron, protons, and CO2, and you have only one machine, and you do. So the two systems are studied currently. The result is that the fuels that we can get from that, or the molecule we can for that, are still too expensive. It is expensive because still the yields are not good enough, but also it's because the electricity is expensive, and the main cost in all this is the cost of electricity. The main cost for hydrogen production is the cost of electricity. The main cost for CO2 to fuels is electricity. So in a future world, if we are not able to produce electricity at low cost, it will be very difficult to electrify all these technologies, including electrical car and so on. So we have really in front of us a big challenge is to produce electricity at low cost. Not only low carbon, but low cost also. Otherwise, we may have plenty of low carbon electricity, but not useful because it will be too expensive.
So if no question, so let's thank Professor Mark van de Cave again.
Thank you. Thank you so much.